Welcome back, guys. So in this week in NanoOptics, we're going to do two sort of quicker exercises. Does anyone have any homework stuff they wanted me to show, or no? Probably not. Okay, that's fine. I would show it if you wanted me to, but if you didn't do it, then it's fine. So the two exercises we're going to do. The first one is designed to show you how plasmon resonances can be used as sensors for basically any type of change in dielectric environment. So, materials interact with light in a specific way, and one way of describing this is with a refractive index. Frequency-dependent refractive index, and so if the refractive index surrounding one of these particles changes, it's actually quite sensitive to changes in that refractive index, and this can be used as a sensor for like binding events, basically. So what we're going to have you do is similar to last week. We're just going to use these kind of built-in shapes here. But the one you're going to want this week is called concentric ellipsoids. So this shows you what it is. It's basically a sphere inside. It's a shell coating a sphere. Okay. So it says there's three sizes that it suggests for you to do in the manual. It says to do 74, 80, and 90 nanometers. In the interest of time, you're gonna have to change this dipoles per nanometer to a much lower value because these calculations take quite a while. So you're gonna want 0.2 dipoles per nanometer, and thus everything needs to be divisible by 5. So every group should either pick one of 75, 80, or 90 nanometers, and those go in this first series of values here. So this is describing the size of the outer, the diameter of the combined radii of the sphere and the shell. Okay, in these ones, and then the second set of boxes here, I think it asks you to set all of them to 70. So this is describing the radius of the inner sphere, which the coating is surrounding. Okay, so the shape that we're having you build using these concentric ellipsoids is. Where did that whiteboard go? I guess there's no whiteboard. Oh. So the shape that we're having to build is a thin shell of gold on an inner sphere of silicon dioxide, or commonly known as silica. And the main reason for this is because these are important shapes in nanotechnology because they're used for photothermal therapy primarily, driven by the nanometallics group at Rice University. And sort of historically these were important structures. So that's why we're having you look at their properties in some more detail.
I was going to upload the SIO too.
No, don't upload it. I'll just show them. I think it's a good exercise. So when you're inputting these, yeah. See, when you do this, it freezes too. So when you're inputting these, it's going to ask you for two dielectric materials now, because one of the things is made of gold and the other one's made of silica. So you want to set dielectric 1 to gold. Now there's no built-in on NanoHub dielectric file for silica. So I'm just going to show you like what these input files look like, and you can basically just type everything into a text file. And so this is how these uploaded dielectric files are structured. So you need 3 lines of header, of which these two are pretty much irrelevant. This is just a name, and this is describing the titles of these columns. This one is important. This needs to read exactly the way it does. So it needs to be 1 tab, 2 tab, 3 tab 0 tab 0. And what this is telling the program is that input 1, which is the wavelengths, are in the first column. Input 2, in this case, is the real part of the refractive index, which appears in the second column. And 3 is telling it that it is the imaginary part of the refractive index, which appears in the third column. Now, the imaginary part of the dielectric function of the refractive index relates to absorption. So we just set this to an arbitrarily low, but not 0 value across the entire visible, because silicon dioxide doesn't absorb light in the visible. It interacts with it, it'll refract light, but it doesn't absorb. And then these columns, so these last two columns are set to 0 and 0, but that just means that we're using refractive indices and not dielectric functions. They're interrelated descriptions of the same thing. So you just need to type, this line exactly the way it appears, anything you want on this line, anything you want on this line, and then type in these values as written here. So 0.3 is 300 nanometers, or 0.3 microns tab. The real value of the refractive index, which is 1.448, and then the imaginary part, which is just a small number. Okay, so basically you can open any text file and then just save this. And then when you get to the part where it asks you to specify the second dielectric function, you can upload that text file that you just made, and then run the calculation. And it asks you to do a series of refractive indices. So I think it tells you to do 1, 1.2, and 1.4 as medium refractive indices. And so basically what you're going to want to do is run those 3 different calculations of those 3 different medium refractive indices. Okay, for one size. We'll get as long as someone does one of the sizes, then we'll have all 3 from different people. So just run it for one size. And then what you're going to want is you want the 3 different spectrum, okay, as a function of the medium refractive index, and then you want the wavelength at which the peak maximum occurs, and you want to plot that against the refractive index. And this will tell you, how does the shift go with the refractive index? Is it linear? Is it superlinear? Is it quadratic, or what have you? And then. So once you get those, and send them to me by email, and then we'll talk about them, and then we'll move on to the next and also last exercise. And I'm going to write my email on the board while you guys are going. Yeah, I can put that. That's actually better. I'll just put that up. Okay, so here's the results of the calculation I was having you run. So this is for anyone who is running 80-80-80, as they say, or conversely, that means a 70 nanometer silica core and then 10 nanometer gold shell coming out from the silica. So shown here is the spectrum at 3 different medium refractive indices. So this purple one is 1, this one is 1.2, and this one is 1.4. Okay, so as you can see, the peak is redshifting, and the extinction efficiency is increasing as a function of the refractive index. And you can see the increase for changing by 0.2 refractive index unit is actually pretty substantial. It's going from maybe 520 up to 570 or so. So that's that's an easily measurable shift in plasmon resonance. So shown here, oh, I should fix this axis, but so shown here is the refractive index versus the shift, and it is in fact linear. You can, it's not too hard of a problem to deduce this from electrostatics. You can solve for the polarizability of an isotropic sphere and get this answer analytically too from electrostatics. But suffice to say, we did the calculation and it worked out. One thing I wanted to point out is I don't think anybody did it today, but yesterday when we were having people run the 75 nanometer with 0.2 dipole spacing, so that's one dipole every 5 nanometers. So then the entire shell is only described by one dipole thickness, and the calculation, generally speaking, fails. You get pretty weird answers, and this is just a result of not having sufficient resolution to accurately calculate the properties. And then at 90, we see a similar trend to what we saw with 80, or if we make the shell 20 nanometers thick, we see a similar trend, and also and again the refractive index is linear. So I have a paper here where someone my boss did very accurate calculations with very high resolution for these, and this trend of shifting in response to refractive index change holds over quite a long series of refractive indices, and this is just shown here what you would have gotten had you done this with higher accuracy, and shown here is how much the refractive index shifts with respect to, or how much the plasmon resonance shifts with respect to a change in refractive index. So this graph on the left is showing you, refractive index or shift in plasmon resonance versus refractive index, and then here this is essentially the slope of that graph. And you can see for these thinner shells, the refractive index sensitivity is in fact much higher. And there's a way to understand this, and it's because if you notice too, like the shell itself is actually shifted from the resonance of a sphere of similar size. It's redshifted, and the reason is so the silica you can pretty much ignore this. This has nothing to do with the plasmonic properties because it doesn't have a high density of conduction electrons. But the gold, so what I actually find is that surface plasmons can propagate on any interface between a metal and a dielectric, okay? And actually in a structure like this, where it's just a shell, what you actually found is that this outer resonance is relatively well described by a sphere resonance. So what this would look like, is conduction electrons oscillating away from their nuclei, and that leaves, sort of an oscillatory positive-negative charge in this case. But because the inside now is also another interface, that can give rise to another mode, and this actually has an analytical solution too. It's just a cavity mode. It's slightly different than the sphere mode, but it does the same thing. And what you find is that these two things can actually oscillate in phase, completely in phase contribution, so that their combined resonances are additive, or they can oscillate out of phase. Okay, and what ends up happening is if you consider these two resonances initially, they're both isoenergetic, and then the hybridization of those two modes, both in an in-phase and an out-of-phase contribution, gives rise to two new modes. One of them is lower in energy, one of them the in-phase contribution, one of them is higher in energy, that's the out-of-phase contribution. But what you actually find is that because in the out-of-phase contribution these resonances exactly cancel each other, you don't see a resonance there. But for the out-of-phase, you actually see a redshift because you've lowered the energy of the resonance. You also see an increase in the polarizability, and so that means that the the overall sensitivity and magnitude of the resonances increase relative to the two isolated systems. And so this is coupling, and this is analogous to many other types of coupling you can think of. Coupling chemistry of orbitals, or coupling of electric fields and other systems. And so to look at this in a little bit more detail, Sarah's going to take you through our last exercise, which involves setting up running some calculations on some gold nanorods that are put in these types of geometries. So the electric field is always going to be polarized along this direction, but they're going to be brought together either end to end or side to side, and you're going to see how the coupling differs in both of these cases. Okay, so I'll give this a
We have some time. Should we run?
Yeah, I'll run some.
Okay, so the Dropbox link that I sent you guys has, so there's no for NanoHub there's no like preset shape in the so I sent you guys some shape files, and those are, there's head-to-head and side-by-side. So head-to-head is the top one where the nanorods are coming together like this, and then side-by-side is where they're next to each other. And then I have the spacing between the two, and that's the surface-to-surface spacing between the two. If you guys want to run a few of these, probably the best thing to do would be to run maybe like 2 head-to-head, and then do one at a close distance and then one at a farther distance, and then just compare the two. Or conversely, side-by-side, do them at a close distance, and then maybe like the 40 nanometers essentially uncoupled. So you're not going to see much of a difference. It's going to look very much like a nanorod by itself. And then for 2 nanometers, you're going to get like maximum coupling between the two. So those would be 2 good ones to run. So then in that case, for the shapefile, you're just going to go to the top and do upload. And then you can upload one of those files. And then the rods are set up as being 2 different components, so you'll want to choose gold and gold for the 2 components. And then you won't need any shape parameters. For dipole spacing, you can use one dipole per nanometer. For the spectral window, about 600 to 1,000 is good, and then you can just run that in 10 divisions. 1 dipole per nanometer should be fine. And then for the polarization, so these are along the y-axis. Make sure that you set the polarization, and then what it's set at is fine, which is Y polarized light. Yeah, 1 second.
Make sure that where it says define polarization, you just click this. So where it should just make sure you click this.
What? No, so it's the Dropbox that I sent.
Oh, like you upload?
So those are several shape files. So the head-to-head and the side-by-side are, yeah. So one of those, or 2 of those, but one at a time. Oops.
Everything else is like normal?
Yeah, so 1.33 for the medium refractive index. The spectral window you want to change to 600 to 1,000. These will be redshifted. You can do 10 divisions. What? Oh, okay. So yeah, the extinction, I mean the scattering absorption, and then also the field, just kind of to see. I guess like the way that the scattering and extinction redshift as you increase or as you decrease the distance between the two would be the most marked thing. Start kind of going over the results. Some people might still be calculating. So yeah, if you ran like one configuration and 2 different distances, you should see significant difference between the 2. I only ran 1 here, but look at the E field. So I don't know why this box is staying here. Okay. I'm not seeing anything. I forget what distance. Oh, well, there it is. Okay, you can kind of see it. Yeah, so you can sort of faintly see, I think the spacing I put here was 6 nanometers head to head. You can sort of see the outline of the rod, but you can definitely see the middle. And it's a pretty high intensity in the middle there. So, I mean, this scale basically scales with whatever your max is. So you're seeing very little intensity because the scale is just very, very high. So, but there's a huge concentration in the middle. And this was head-to-head 6 nanometers apart. I think it was 6. Okay, so I have the spectra here for So I have the scattering spectra. You would see something similar with the absorption for head-to-head orientation. I didn't include the zero. The zero is actually just sort of to show that at that distance, the coupling model doesn't apply, because you have other effects. You have like you could have charge transfer, and the coupling model sort of breaks down at that distance. But I have probably the best one to initially look at is 40 nanometers apart. So in this case, we have two nanorods that are head-to-head, and our polarization is along the y-axis. And the mode that we're seeing is basically this mode here, where we have plasmon along the long axis of the rod. When the spacing between the two of them is 40 nanometers, you essentially don't have coupling between the two, because the coupling decays exponentially with distance, and you're basically going to see essentially isolated rods. So in this case, the peak scattering max is at around 800. When you bring the rods closer together, you start to see coupling between the two. You start to see an interaction. And then you get a shift of your resonance to the red. So when you bring them 14 nanometers, when they're 14 nanometers apart, you have a peak scattering max of 820. And then at the maximum coupling shown here of 2 nanometers, you have a peak scattering of 888 nanometers, so a significant redshift in the mode. And basically what is causing this is similar to the case of having the nano shell. You get basically a favorable interaction between the resonances. So in this case, you have two rods. And when you bring them together, you see there are two different modes that can occur. Basically, you can get the resonance oscillating in phase, and you can get the resonance oscillating out of phase. This phase is a favorable interaction. It increases the polarizability of each rod, and therefore it is lower in energy. And that is what gives you the resulting redshift that you see. This interaction is higher in energy. It decreases the polarizability of the rod, and it will give you a blue shift if you see this mode. But because these rods are identical and the resonances are identical, you won't see this mode because the plasmons will cancel each other out, or the dipoles will cancel each other out. So you don't see this mode, you only see this mode. And that is what's giving the significant redshift. The redshift just increases as the coupling increases as you decrease the spacing between the two. So the other case was when you align the rods head to head, or side to side. Okay. So in this case, 40 is still our uncoupled mode. So in this case, when we see nanorods side to side, 40 nanometers apart or uncoupled, we should basically see the exact same thing when they're head to head and 40 nanometers apart, because they're essentially not interacting. And there is a very small amount of coupling because it's not identical, but it is around 797, so it's around 800. So we basically are still just seeing the longitudinal mode of one isolated rod. But as we bring them together, we see something similar when they're head to head. So when we bring them together side to side, they can also interact in two ways. They can interact out of phase and in phase. In this case, though, when they're out of phase, that is a more favorable interaction. interaction, and that will increase the polarizability of each dipole in each rod. And when they are in phase, that is an interaction that's higher in energy. It decreases the polarizability. In this case, though, this is the mode that we don't see because the dipoles cancel out. And this is the mode that we do see, which is a higher energy mode, which is why we see a blue shift. So as you go from 40 nanometers to 14 nanometers apart, you see a blue shift to 777. And then at the highest amount of coupling, 2 nanometers apart, you see that the peak scattered max is 735. So you see a pretty significant blue shift. Yes, so it's very similar to the type of coupling that you see in the gold shell from the previous example. What? Oh, the field. Okay. So I just have a couple field plots. So this is 2 rods, 14 nanometers. So here you can actually see the resonance from like the rod, the single rod with intensity at just the 2 points of the rod, because the coupling in the middle is not quite as strong when they're farther apart. So just the intensity scales to come in. But you do see that the highest intensity is at that junction between the 2. And then when they're side by side, remember we are still exciting the longitudinal mode. So, so in this case, this interaction between the 2 is unfavorable. But the field intensity points are still at the tips of both rods. So a configuration like this is one that if you were looking for something where you had a very high field intensity, if you were doing circuit dance Raman or you were trying to get increased dielectric sensing, this would be the type of configuration you'd want, because you get taking this sphere and elongating it into a rod also will increase the field intensity that you get and localize it on the tips. But coupling between multiple rods will give you a much higher field intensity, and it will allow you to localize the electric field on the surface that you get even more than you would with an isolated rod. Yeah. Do you have anything to add, Jeremy? Okay. All right.
Yeah, actually, I have one thing to add. We're going to post that Dropbox link that she sent you. We're going to post all of the answers to all of the different exercises for the whole week, as well as some literature references if you're interested in that Dropbox. So sometime later in the week, we'll post like all of the the shape files and the Excel spreadsheets showing the various effects.